we now know enough to think about a circuit, a very basic circuit. And let's even give it a definition. Why not? Circuit needs a definition too. How about current flows around a loop? There you go. Anytime current flows around a loop, we'll say that's a circuit. If I were going to draw a circuit in the real world, in a little cartoon world I live in as a physicist, I would draw something like this. Here's a battery. It's got a positive and a negative terminal. That's where the battery does its electrochemical work to make current flow from one side to the other. It's probably got some wires on it. And I would want those wires to eventually go to something. The circuit has to do something interesting. So this would be something with resistance, because something exciting needs to happen. And then, oh, but we have to go in a loop. The current has to make it back around, so I'd probably bring that wire back to there. So we got a battery, we got something with resistance. What about the wires? We've got to think about the wires a little bit. These are very conductive metal wires. Okay? So in terms of currents and voltages and resistances, you ignore them. The current just flows through here. You pretend there's no resistance, there's no voltage drop, there's no electric field. You pretend they're just ideal little wires. Because pretty much they are compared to this. This has some big resistance. These have essentially no resistance compared to that. So those are just sort of conduits. Think of them as ideal conduits. That's how I would draw a circuit. And if I were trying to make the circuit for an iPhone, this kind of a drawing would get messy pretty fast. So of course, engineers have real ways to draw circuits with circuit symbols and circuit elements, everything. So let's draw this circuit with circuit elements. Well, first you need a battery. So that is the symbol for a battery. Two lines, one line longer than the other. The longer line is positive, the shorter line is negative. And I think it's meant to represent the plates in an electrochemical cell. And sometimes you get more than two. You can stack up those plates to get more potential difference. So there's your battery. The wires you draw pretty much the same. Just a thin line means a wire, means no resistance, no voltage drop, no field. But you don't draw them all curvy and crazy. You draw them kind of nice and square like this. And then you come down and your resistor is a squiggly line like that. Not squiggly, but it's actually a zigzag line. So this is the resistor. This is the thing with resistance. We've also learned about another circuit element, capacitor. But you gotta be careful, it looks like a battery, except that the two plates are the same size. Because a capacitor is a parallel plate capacitor. This is a capacitor. In these two circuits, the same thing happens. Current flows from the positive back to the negative. Same thing over here. Current is going to flow this way through the resistor and then back to the negative side over there. Okay? So if you, in this class, in this online class, we're not going to do labs and detailed circuits, but I imagine that many of you will eventually do detailed circuits if you take a class on a campus or some other online class with a lab component. So if you do, you're eventually going to have to make circuits on a breadboard. So this is the breadboard that would be in the lab. It is just a big box with holes in it and electrical connections. So I think conceptually, it's not that hard to go from this loop circuit to this loop circuit. But then when you go to this is more difficult. So let's have a look at it. Even though we're not doing a lab for this course, I want you to see how it works, give you some idea. So it's a big thing with holes. First, the power supply. So we don't really use batteries when we make, well, when we design circuits, we use a power supply that's hooked up to the building power. And that gives you your potential difference. So here, this one, you maybe can see the little ground symbol. You think of that as 0 volts. And then this is at plus 15 and minus 15 and 5 volts. So you could use these two as your first two wires to get 0 volts and 15 volts. And then you take a resistor. So here's a 2.2 kilo ohm resistor. And you would then have the 15 volt wire come into a hole, and you'd put this thing in a hole next to it, and then you would put this end in yet another hole, And then you take the wire from the ground and put it in yet another hole. And if you hook it up right, it's actually not that different from the drawing on the board. Okay? So current is going to flow out of the high, V high, and go through this wire. And if it's hooked up right, go through the resistor. And if it's hooked up right, go into the black wire and then back down to ground. So it is still a loop. When you get into complicated circuits, it may not be set up to be a nice pretty loop. It may be a big mess. So the key to being able to do this is understanding the holes. Okay? So here is a small breadboard. On this one, it's the same pattern. It's always little spaces of 5 lateral holes, and then you've got a big long line of holes on the side. So these little groups of 5 are all connected. So if you want to hook two things up, you put them next to each other in a row of 5. The long ones down the side are actually connected all the way down, and those tend to be for power or for ground. So if you're a visual learner, what I'm going to do is take this apart so you can see the connections in the back. Okay, so let me just take this thing off of its plate real quick. And one more. And I did it already ahead of time and peeled off some of this paper. And now you can see those little groups of 5, they are connected. This metal plate is what's connecting those 5 holes. And if you look down the side, sure enough, it's not just connected 5 at a time. This whole strip down the side is all connected together. So you could put your plus 5 volts there and put your ground there. And then when you want to connect to things, you do it in the small groups of 5 holes. For example, if you wanted to hook up this little operational amplifier, these little just circuit chips like this, you shove them in the holes like that, and now you've got independent access to all these leads and access to all these leads by hooking into their groups of 5 row there. So that's just to give you an idea. So now the first time you see this thing, there's no need to panic. You're just using the holes to hook things together. And in principle, it is the same as our current loop, our circuit loops. We can look at our circuit again. Now that we have it drawn this way, I'll draw it with circuit elements like this. So just our battery and our resistor. And define a few points on the circuit and really think now carefully about what's happening to a charge carrier. So point 1, point 2, point 3, and point 4. Those are the critical parts. This battery gives us delta V bat. We know the long line is plus and the short line is minus. All we need to know. So let's imagine a positive charge carrier. And what happens to it in its life in this circuit? Let's start at 1. It's just sitting at 1, minding its own business. It's just sitting there. We define it to be at 0 volts. Just like when we were doing potential calculations, we said we'll call infinity 0 volts. You always get to call somewhere 0 volts. So we are going to say right there, we're going to call that 0 volts. When it goes from 1 to 2, the battery does work to raise it to V bat. We don't have to call it delta anymore because we've defined 0. So it went from 0 volts to V bat volts. Okay? From 2 to 3, it flows. So current, it flows. Actually, we're thinking of a single carrier. Let's not call it a current. The carrier flows with no drop in potential. It does not lose any potential energy because we think of these wires as perfect. The charge carriers just move in them. They don't dissipate any energy. They don't lose any energy. They just move. It's not really that perfect, but basically it's a lot better than the resistor. So the metal wires we think of as perfect wires, and we just think of a simple circuit. And then it goes from 3 to 4. And here we would say the carrier, it flows through the resistor and it loses a potential delta V equals what? Equals the current times the resistance. Delta V equals IR, like we calculated before. So you can apply that to this individual thing. So it does lose energy there. It goes from a high potential to a low potential. And we thought a little bit about where does that energy go? It goes into heating the resistor. And then 4, and then let's see, 3, well, and then at 4, it sits at 4, and it's back where it started. Okay? That's the cycle. Now, a lot of that was not exactly what's happening, right? Because these circuits use metal wires. They're really metallic conductors. So we say, oh, well, we have current always goes from plus to minus because that's what a positive charge carrier would do. Well, in reality, we have electrons. And electrons are negative, so they actually go the other way. So in this circuit, in reality, it's electrons flowing like this. But we think of it as current flowing like this because we think of current as positive charge carriers. Or we define it to be a positive charge carrier when in metal it's really negative. So you want to keep that difference. We've mentioned it before, but really keep that straight. Even in electronics, you got to keep that straight. When I was on my coffee break, somebody actually sent in a question. They said, just, we're not microscopic enough. I really want to understand everything microscopically. And they were bothered by this wire. What's really going on when you say there's no resistance, when we think of the wire as perfect? So let's look at a sort of a Drude model idea of what's going on. Let's draw a nice, good conducting wire section that then hits a resistive section and then back to a conducting wire. Right? So this is good wire, and this is resistor. And this is wire again. So we talked about it in the circuit. We said it flows, no potential drop, meaning no loss of energy here, then all your losses here, and then no loss here. But let's think about what the charge carrier really is experiencing in its real life, okay, as it moves along. Okay. It's the same current flows all the way through, okay? So we have some current flowing through here, it's flowing through here, and it's flowing through here. And in this case, they have the same cross-sectional area, so they all have the same V drift. They all have the same V drift. Because remember, V drift was the volume density of carriers times their charge times the area times V drift. And all those things are the same. It's just a similar cross-section. It's just that here inherently something is different to make it a resistor. Now, since this is a good conductor, its tau is very large. So it can go a long time between collisions. But it has to maintain the same V drift because the same current has to flow everywhere. If you had current flowing different amounts in different sections, you'd have charge building up on the surfaces. That's not what happens. It just flows. So this thing has a large tau, and it has to maintain the same V drift. It must be something kind of like that. Okay. This thing is a poor conductor. It's our resistor. It has a very small tau, okay? So it collides very often, but it has to keep about the same average velocity. So it must do that. And then back to the wire, it must do kind of like that. Okay. If you're going to have these two things be different in this way, that this one has a very infrequent tau, and this one has a very frequent tau, that's pretty much how you have to draw it. Okay? If it's going to collide every so often, it has to get up here to make the average be there. That's what it has to look like. There's that one's tau. But let's think about what we said about what's happening inside the material. This one has a low acceleration, is a long time to get to the same velocity. It's a low acceleration. Right? You can just see it. That slope is low, and here, in here, it's got a high acceleration. For the carrier to get up to that average velocity every time between these frequent collisions, it has to accelerate really hard, and then here we're back down to low. That acceleration comes from the field. What that means is here you have a low E field, and here you got to have a high E field. Because that's what sets. Remember, this is QE over M. Q is the charge, M is the mass. Those are constant. It's the electric field that's changing. So if you want to think about this, as you go through the wire, what's actually happening is you have a teeny electric field here, and you have a big electric field here. Then you have a teeny electric field again. You get a smaller electric field in the wire because it doesn't need a very big electric field to maintain the same drift velocity of the charge carriers. Because they hardly ever collide, just a little bit of electric field accelerates them really fast, and you don't need a big electric field. Small electric field means what? It means a small potential difference. So if you have these equally linked spaces and you're trying to make different fields, they have the same distance, so this would need a lot more potential drop than this one. And that's why we say the potential stays basically constant through these wires. And then all your potential drop is here, and then the potential stays pretty much constant in this wire. So if you want to think of it in terms of Drude, you can think that, well, basically, you don't need a big potential drop because you don't need a big E field because the collisions are pretty infrequent. You don't necessarily need this to understand a circuit, but you can really go that far to really understand microscopically what's happening in these circuits. Our final topic for this little circuit we've made is power flow. Circuits really just have electrical energy flowing through them. If we draw this circuit again, one way you could draw what's actually happening is that power is flowing from the battery out through the resistor. So let's think a little bit about what each element is doing. The battery does work on the carriers. It's doing a certain amount of work per unit time by bringing the carriers from zero potential to a higher potential. And then the current creates heat in the resistor. That's the other place there's a power flow in the circuit. Gives the energy to the current, and it loses it in the resistor, and all those little collisions, all those little Drude action collisions happen and creates more heat, like you've learned about. So let's look at it quantitatively for a minute. Let's think about the battery. The power is sort of the change in energy per unit time. We'll call it du dt. And what it's doing is taking carriers of charge Q and giving them a potential difference, delta V. It's raising their potential. So that would be d times their charge Q delta V dt. And this is a derivative of a product of two things. So you apply the product rule. That's going to be delta V times dq dt plus q times d delta V dt. So you can look at those and say, what is this? Well, this is delta V, and dq dt is the current. So that's delta V times I, if you think about what's happening to individual ones. And then here, d delta V dt, well, delta V is a constant. That's the battery applied, or that's the potential difference applied by the battery. So this is 0. So we see that the work, or the power by the battery, P, is I delta V. It's the current times the amount of work, or the potential difference you carry it through. And it makes sense. If the work it does on a single carrier is its charge times delta V, then the rate of work, this is just the rate of charge, that would make sense. This P equals I delta V applies actually to any circuit element. You can also think about the resistor. The current flowing through it times the delta V that you lose, which in this case is equal to what you gain in the battery because there's nothing else in the circuit. That's how much energy, or that's the power that you lose that goes out to heat. Okay? Sometimes you see it written different ways. You might have a circuit where you just know the current and you just know the resistance. You want to know the power. Well, you could use V equals IR here, and that would be I times R. So P is also often written I squared times R. Or you could get it in terms of V and R. If you just know the potential and the resistance, you'll get that it's delta V squared over R. Between V, I, and R, there's several ways you can write the expression for power. So let's look at power in a circuit. Here, remember, we have our little power supply, and the wires go to this little resistor. So if you want to see the power, you turn it on. That's pretty boring, right? So you don't really see anything because, well, just trust me, there's power being dissipated in the little resistor. But now let's do something more exciting, okay? So here is another little resistor. This is something they used to use a long time ago as a source of heat. It's a nichrome wire, a very long nichrome wire. Nichrome has a high resistance that you actually plug into the wall. So nice fat copper wires here don't have much resistance in them, but then it goes to nichrome, huge resistance, so all your power is dissipated in this thing. And if you plug it in, it generates so much heat. You have so many little Drude collisions in there, exciting the lattice. It gets so hot, it actually glows orange, and it feels really warm. And you can use it to heat your room. You don't usually have it sitting out in the open like this. Usually you have it in sort of a little lens shaped thing that kind of radiates the heat out into the room. But that's what this is. So now you can see it starting to turn orange. This is one of my favorite demos because it can both shock me and burn me at the same time. It's extra dangerous because this is line potential right out here in the open. I have it hooked up with an ammeter in series, so this is basically just a little instrument that's measuring the current. Okay? And you can see it has a current, I think, of around 5.5, around 5.5 amps, something like that. And now you can literally see the power being dissipated. So what we're going to do now is change things a little bit. We talked about how resistance depends on temperature, or resistivity depends on temperature. So if I could change the resistivity of this wire, we can see what would happen. What I'm going to do is this. So if I blow on it, you can see it cools off. It's not glowing anymore. I'm changing the resistivity. I'm changing the resistance of the wire. And we can see what happened to the current. So the current, I think, was about 5.49 or something, 5.47. So I blow on it, spit on it a little bit, that cools it off, and the current goes up. So we can say which law makes sense, what's happening. Oh, it's here. It's V equals IR. That's what explains it. Delta V equals IR. We're applying a constant delta V. The wall is giving us 115 volts. It's actually AC, but don't worry about it. 115 volts here. I blew on it, and I made the resistance go down. Therefore, the current had to go up. If we thought in terms of power, we would want to go here. The delta V is constant. I blew on it. The resistance went down. Actually, it dissipates more power when I blow on it. I cool it off, and it actually ends up not as hot. It's not orange, but it's actually more power gets dissipated when I'm cooling it than when I let it just sit here and get to equilibrium. So anyway, this is just an element like this, which I don't recommend you play with, is a way that you can really see and think about power dissipated in a circuit.